All right, welcome back. So here's the AdaBoost algorithm again. How can we understand how this whole thing works? Why is it that, theoretically, why is it that this thing is quite a good classifier? Well, let's start by looking at the training error. All right. So the first thing you want to know about a classifier that works at all is that does it minimize the training error? Because if it doesn't do that, it can't do anything. Well, how can we find out how good the training error is? Well, we can go ahead and bound it. We can find an upper bound, something which is always bigger than the training error, and by necessity, something that we can analyze, right? So if we find an analyzable function that we know is going to be an upper bound, something somewhat bigger than the real training error, then we can guarantee that training error is always at least below this point, right? So let's think about this for a second. At every point, our error is going to be the 0, 1 loss, right? So however many errors we get, what we're adding up is how that many ones on the 0, 1 loss. Okay, well, we can bound the 0, 1 loss, as we know, by a set of functions that happen to pass through the same point right there, but, are analyzable, unlike the 0, 1 loss. So in this case, we're going to use the exponential loss, an exponential which passes through the y-intercept at 1. Okay? What we say here at this point is that the exponential loss is a surrogate for the misclassification error for the 0, 1 loss that we actually want to investigate. Okay? It enables, it's going to be a stand-in for us. Right, so if boosting can make the upper bound approach 0, then we know the training error has to approach 0 because the training error, the real training error, is squashed underneath that. Again, the total training error over a data set is going to be adding up all these ones, right? If we add up all the values of the exponential loss, we know because it's higher than the 0, 1 loss at all points, right? Then we know that it is going to necessity be higher than the 0, 1 loss. The exponential loss always has to be higher than it because it's higher than it at all points on the line. Okay, cool. Also, the other balanced, other side of this is that, of course, the exponential is a convex function. So if we want to know where is the final value of the training error, we can look at it by looking at the weight update rule. Okay? Works a little something like this. So we know that here we have, let's use this. Right? This is, in the beginning, we have an equal weighted data set. And the misclassification error is just, in the beginning, is what I've circled. So we know that, so what we're after here is that we're going to apply the weight update rule, okay? So we're going to start off with the 1 over m term. And we know that the first classifier is going to make some errors. And those errors are going to be, we're going to update the weight rule according to those errors, right? So we're going to put in the e to the minus alpha y h sub 1 of x. There's also this normalizer z1. Okay. The next time around, this is going to update the weights multiplicatively. So we're going to do this again. We had been updated by the first classifier. Well, now we're going to add in the second classifier. Okay, so the weight update from classifier 2 to classifier 3, we're going to do the same thing again. It's a multiplicative process. All right, well, it turns out that the whole thing is going to end up approaching exponential of minus y sub I f sub x. Why is that? Well, we know that the overall, remember, let me go back one, right? We know that the loss is less than the exponential because at all points the exponential is above it. So we know that the total loss here can be replaced by the exponential. And that would be a less than equal to situation like we see here. Okay, and multiplying these e's through also suggests that same thing that the exponential goes to. Now finally, the z's on the bottom, these again are normalizers to make the whole thing, whatever the d is at any given time step, the summation of d sub I is always equal to 1, right? Whether it's at d1 or it's also true at d2 and d3. So the z's are picked at every point to make that happen. Right? So those z's are multiplied too, so we get a product of z's. Now, right, so because of that, because all the points sum up to 1, we know that the only way for that to happen is for this product down here to be the same as this numerator here, right? We have to have the exponential and the product have to be equal. Otherwise, you don't get the summation up to 1. All right, that's how we get to the point where we know how we're going to handle this. Because this exponential is, we know the upper bound, and we know that to get this upper bound, we have to look at the product of the z's, of the normalizations. All right, so again, the upper bound is the thing that's going to drive us down to 0, and we're going to be able to say that as long as z of t is less than 1, then the training error has to decrease exponentially. Why is that, right? If z of t is less than 1, then the product of z of t is got to be going towards 0, right? If z of t is always less than 1, then multiplying by less than 1 means we're decreasing the number, and we're continually decreasing the number as we add more and more classifiers as the number t gets higher and higher. Well, if we're exponentially approaching that 0, that's good news. This upper bound is driving downwards. Okay? So more to the point, this kind of thing, right? The z of t, again, has to be equal to the numerator. So the numerator looked like this form. So this is why z of t has the same form. It's the summation of over all the data samples of the weight for the sample and the exponential, alpha, the proper output, and the predicted output. So what we can say is that what we want to be able to do is we want to be able to pick alpha to make sure that z of t is less than 1, so that we're driving this thing quickly. And I will say to you that, without getting too into it, that this is the alpha that you can pick to do that. And you can kind of see how this works, but I'm already spending way too much time on this stuff. But let's just kind of realize, to understand how it works, that, with this y of I in there, that's how we deal with both positive and negative misclassifications, right? Well, if we want to get rid of that y of I, we can break it up into two terms. That z of t is the positive misclassifications and the negative class misclassifications. Sorry, my bad. I said that wrong. These are the misclassifications, and these are the ones which we don't misclassify. So this is bad, and this is good. Right? You can see that there. All right, so if we can break it up into those two parts, then the next thing to remember is that the summation of d of t is 1. And because the summation of d and t is 1, those go away. So we drop out to the, right? Oh, and because they go away, the total count is the error rate, right? So the whole thing, the summation is counting up over the number of errors. So we get the number of errors here, right, times the e to the alpha t. And then everything over here on the not misclassified side, right, is going to be 1 minus the error rate times e to the minus alpha t. All right, so to find the best alpha, we want to drive this thing as quickly as possible to 0. So we set the partial of z of t, we want to get it to its minimum, and it's a convex function. So to get the minimum of the convex function, which has got to be at 0 in this case, well, we just want to set the derivative equal to 0. So we go ahead and do that, and we can solve for this, which once we solve for that, will lead us right back over to here, to the answer. Amazing, yeah? Yeah, this is some pretty complicated stuff. If you think I knew this off the top of my head a week ago, you are wrong. I always have to sit there and look at this, and I get confused, and it's okay to be confused. But it is a pretty neat set of tricks. All right. So we can also do one more cool trick, which is to take this form and this time put it in this form, which is going to be very useful to us in 1 second. So if we want to know in the end, how can we be sure that this thing is going to drive training error to 0? We're going to rewrite the error terms. So we're going to write the error term as two parts. This is a binary classification task, right? So what is chance performance at a binary classification task? Yes, Marilyn Monroe. You're right, half. 1/2. Okay? So how much better are we going to do than chance performance? Well, if our error rate is less than 1/2, then we are doing better than chance performance. So we're going to use gamma here as our how much better than chance are we doing. So gamma of t is for classifier t in the sequence going 0, 1, 2, blah, 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 right? That is how much better than chance. All right, so here you see on the screen that form we just arrived at in the last slide. We know that the total final training error has got to be less than the product of z of t. And we know that z of t can be reduced down to this form. So we can plug in the 1/2 minus gamuts of t into every one of those epsilons, and we get this form. And well, if we keep simplifying that, we can eventually realize that this has got to be an exponential of minus 2 summation of the gamma t's. Ooh. So that's got a cool property, because that means that the training error in the end has got to be less than an exponential with a negative sign on it. And this summation is the summation over all of the classifiers. So as we get more and more classifiers, that sum gets bigger and bigger. And that sum, like I said, this gamma here, right? This gamma is how much better than chance are we doing? As long as that gamma is greater than 0, as long as we are doing better than chance by even a tiny amount, adding more classifiers, right? Getting this summation here going further and further. So the notation here is that capital T is, the thing here. So actually I should do it this way. So T equal to 1 to capital T, right? We're going to go for a capital T of these guys. So as long as capital T is a relatively large number, even when gamma is tiny, just as long as it's above 0, we're going to start approaching 0 because the exponential is a negative exponential here. Very cool. So it approaches 0 as t increases whenever gamma is greater than 0. But what, you ask, about the test set error? Because all we've done is prove that the training set error is going to approach 0. Well, what do we normally expect as training set approaches 0 error? Well, we expect overfitting, right? We know that the testing error is going to be less than or equal to the training error plus generalization, right? And generally, as we've talked about, stuff like in probably approximately correct junk, in that computational learning theory stuff, what we've done is we were trying to figure out bounds on things, and you can get a bound on generalization error. So this is the kind of picture we expect, right? As training error approaches 0, our test set error is going to drop 2 until some point when it stops dropping, and we are overfitting, and we start overfitting the noise in the data, and the test set error goes up, up, up. Okay, so the training error continues to drop or maybe reach 0, but the test error, at some point, the final ensemble becomes too complex, too powerful, and it overfits the data. Well, we don't actually get that when we look at boosting quite a lot of the time, I should say. It's not that we can't get that, because of course we can overfit, but boosting is surprisingly resistant to this problem. So here is when they boosted C4.5 trees. Right, so we used the C4.5 tree algorithm. These were full trees. They weren't stumps. They were full trees. So each one of these trees can get kind of big. Okay? And they were using the letters data set. This is an example of the letters data set from UCI. Right? Each one of these, there's like a base letter in there, and the letter is stretched like taffy in 9 different ways from Sunday in a random way. So what happens on that data set is that the training error drives to 0 as we expect and stays there. But the test error does not go back up. We expected something like this, right? Doesn't happen. So, and that's true even after we've gone through 1,000 rounds of classifier addition. So there are 1,000 classifiers in the ensemble. And if you count up all the nodes in all of those 1,000 trees, it goes over 2 million nodes. So this is a crazy complex classifier. Why doesn't it overfit? So anyway, these are just the data to go along with what I told you. The training error drives to 0, and the test error doesn't drive to 0, but it also doesn't go back up again. It drives down to a low level and stays there. So you would expect that too complex a classifier is a bad thing, right? We generally prefer the simpler of the possible classifiers using Occam's razor. Well, before I can get to why the training error stays up, I just want to introduce one other cool property of these things. All right, so you can identify outliers in the data set using a boosting method. Why is that? Well, every single time you misclassify something, you are going to end up focusing more and more of the next classifier's energy, I guess that's the wrong word, but effort, right? We're going to take more of the next classifier's in line's effort to try to make that right, okay? So what's going to be hard to classify? Outliers are going to be hard to classify, right? You're going to draw some decision line that does the best job, but if there's an outlier, if there's something way out here that you just can't catch, then it's going to get a higher and higher sample weighting. The sample weighting out here is going to go up and up and up on all those outliers for every new classifier you build. So what happens there? Well, it's cool. All you have to do to identify outliers is look for those data samples which have very high weights at the end of the process. What's bad is that going through all that can degrade the classification performance dramatically, because you can never fix the situation, and it can really increase the time it takes to fit all these things, because you're just going to keep fitting more and more classifiers, and potentially, depending upon the classifier you use, when you have like an SVM in there or something like that, you would have a hard time, with a high C, that would make it hard to find that with outliers. Okay. So now that we know we have outliers, and that I should have mentioned, one of the things here is that the thing about a outlier is that we can talk about it as having a large margin, right? That the distance from the decision boundary here for that outlier is a large one, okay? So that is the final piece of the puzzle to talk about testing. So this paper has this result, which I absolutely do not have the time nor inclination to discuss with you because it goes into some fairly deep statistical learning theory. Just of note is that this is the VC dimension, and this is the size of the data set. Okay. And what this paper shows, which I'm just going to write down and not solve here for you, is that when the margin is large, that you can end up getting a situation where it aggressively concentrates on those hardest examples. Okay? It's going to keep increasing the margin until it concentrates on those hard outlier examples. And when the margin is large, more weak learners are going to agree because you're going to keep stacking them deeper and deeper. And in the end, what's going to happen is, even though you're putting out more classifiers, those classifiers are all agreeing with each other largely. And so the overall ensemble is not getting more complex because there's no diversity. All the new classifiers are roughly doing the same thing. And that's why we don't end up, if you you're not actually getting a more complex ensemble out of this. You're just stacking more and more classifiers into it that roughly do the same thing. Okay? So we can still get overfitting, but it only can happen when the margin is too small, when there's no outliers, or if the weak learners themselves are ridiculously complex. All right, let's finish up here. So let's compare AdaBoost versus random forests, right? So on the left, we're going to have the random forest bagging world, and on the right, we have AdaBoost and the boosting world. So one of the main things is right off the bat is that bagging resamples, right? So you're going to get a different data set in every classifier. In AdaBoost, we don't resample, we reweight. It's the weight that we change from classifier to classifier. So there's no weight in random forest. There is one, and it's a function of the classifier's accuracy in AdaBoost. Random forests, to prevent overfitting, you generally do have to have some kind of enforced weakness constraint. Okay, you want to make sure that the individual trees in the forest don't grow too large. You'll average them out, but you'll just do better if they're weakish, and also, but not too weak, right? So boosting in general cares much less what each individual classifier looks like. As long as the individual classifier is not so ridiculously complicated that it can overfit by itself, then we don't really have a problem with complexity. And we also don't have any problem with weakness as long as we know that we can get at least a smidgen, just a tiny, tiny margin better than random chance. All right, so it turns out that random forest doing that resampling is going to reduce variance on the bias variance trade-off. Okay, we're going to average out among all those trees, and that's going to reduce variance. But with AdaBoost, both bias and variance are reduced because we'll keep getting better and better and getting more and more complex until all the weak learners start to agree with each other. Finally, just implementation-wise, there are some issues. So random forests are about as fast as you can get. And as I've mentioned in the past, random forests are generally a good enough situation, right? For most real-world kinds of things, a random forest set up properly is a good enough solution, and it's a very fast solution. Random forests can do feature selection. Boosting things, including AdaBoost, is a sequential implementation. It is not parallel. So we can't just split it up and let a different processor do every single classifier because we have to finish classifier 1 before we can do classifier 2. So boosting is slower. It is generally a higher level of performance than a random forest. Now, outlier, it can't do feature selection, but it can do outlier detection. And neither one of these algorithms is really interpretable. It's, like a tree is interpretable, but the interactions between the votes among a bunch of different trees, much less easy to see how an individual variable contributes to the final decision at that point. All right, so I'm going to take another short break. At this point, I've already used up all of my allotted lecture time, so I'm going to consider the final section, which is on gradient boosting, to be kind of optional for everybody, but I'm going to go ahead and record it anyway. All right, have fun. See you in a minute.